Okay, so if you draw a line from the origin to the power required curve, then the angle that line makes with the horizontal tangent of that angle actually gives you the thrust required value. And if you think about this, the angle becomes minimum when the line becomes tangent to the curve. So this is the minimum possible angle you can have. So this the tangent point corresponds to the minimum thrust required value, and the minimum thrust required value, if you go up to the thrust curve, it corresponds to this point, the minimum thrust required point. Okay, so later we will see that these will become important. For example, if you want to calculate the range of a jet aircraft, for example, you draw such a line and then say that, okay, so this is the speed for that. Or if you want to calculate the minimum endurance for a propeller aircraft, I'm just making it up right now, but that's when you will be using such geometric analysis from these curves. Okay? Okay, so let's see. So the discussions from before are valid for all types of engines, and the efficiency expression we drive is valid for all types of engines. And here you see the common engines used in aircraft today. The first one is the reciprocating engine. This is just a piston engine, just like the engines in our cars. And that engine is used to rotate a propeller, and the propeller creates the thrust force. And the other type is the turbojet engine. In this case, in the propeller, the thrust comes from the propeller, and in a turbojet engine, the thrust comes from the jet created by the engine. And then these are sort of combinations of the two. So in a turbofan engine, you have a jet force plus a propeller-like device in front of the engine. So the combination of the two creates the thrust force. And similar to turboprop has a very similar. In the turboprop, a turbine engine drives a propeller instead of a piston engine, and that propeller gives you the thrust force. So these are the two we will be talking about in this course. Okay, so these have different performance characteristics. If you have a propeller creating the thrust force, then it has certain performance characteristics. The other option is the jet. You add kinetic energy to the air, and that jet exiting the engine gives you the thrust force. Okay, so these are the two types of engines we will consider in this course. So if you look at what's special about the two, in propeller you have a large diameter, right? In the propeller, let me just try to draw. In the propeller engine, you have some engine here, and then you have a large propeller. So and the propeller gives you the thrust force. And in the case of a jet engine, you have so this is how you get the thrust force. Typically, if you compare the two, for a similarly sized aircraft, if you want to use a propeller, the propeller will have a much larger area compared to the area here. Okay, so the propellers have a large diameter, and that allows them to move large amount of air. That means m dot is larger, but gives air a smaller acceleration. This makes the propeller engines more efficient, so they are highly efficient, but they are low thrust. And the thrust is limited by propeller tip speed. So if you use a propeller, since you have a large diameter, that makes your propulsion system more efficient. But the downside of using a propeller is you cannot create too large thrust forces by using a propeller. So propeller engines are ideal for low-speed aircraft. If your aircraft is flying on the order of 0.5 Mach or less, then using a propeller is a very good idea because you will have a very good efficiency. But if you want to be able to fly faster, then if, for example, modern airliners fly around 0.85 Mach, and at that speed you cannot use a propeller. And the reason that is you reach supersonic speeds at the tip of the propellers, and due to supersonic speeds, rotating a propeller requires too much power, and that reduces the efficiency and makes it really impossible to use a propeller for very high speed flight. If you look at the jet engine, you have a smaller diameter. That means the m dot value is smaller, but you can give air a larger acceleration, and due to that it has low efficiency, but you can create more thrust using a jet engine. So let me show you some videos explaining how a jet engine works. Okay, so here I say that you add kinetic energy to air, but if you want to see how that happens, let me show you these videos. Well, there's a better video. I think the second one explains it better, so let's take a look at that.
A turbofan engine is a complex synchronization of several components working together as two parts. A core section that produces power to drive the propulsor section that produces thrust. Thrust is a force created by the acceleration of air. This phenomenon is simply an application of Newton's second law of motion, commonly expressed as force equals mass times acceleration. It is this force that propels the aircraft
So actually the engines we saw in these videos are turbofan engines. So they are like a combination of propeller and jet engine. So if you paid attention, so this is propeller. Jet engine, but in a turbofan engine. So you have a combustion chamber here, you have a compressor here, and the turbine here, and then there's another fan in the front. So this is the overall engine. So this is the total air coming in. So it's divided into two parts, right? A part of the air flows around the core section. So it flows through the fan here. So let me call this M1 dot. And then the other part that goes through the middle is M2 dot. So let me call this VJ2. And then the air leaving here is VJ1. So this M1 dot is larger. So this is what they call the bypass ratio, the ratio of this air to this air, the bypass ratio. So the air flowing around is the more efficient one. So this is the one that flows through the fan, which is very much like a propeller. So this produces 80% of the thrust, right, in that engine. And the smaller part, this one produces 20% of the engine. So this is the M2 dot. This part is like a jet force, and this is the other part is like a propeller force. So they're doing this to make it more high performance, basically. So they can create larger thrust forces when needed, and then the efficiency is as good as possible. So this is how a modern turbofan engine operates. But in this course, we will not consider turbofan engines at all. We will use either a jet engine where we only have the middle part, no fan in the front, or we will use a propeller where we have this part only and no middle part. Okay, so but you should know that in modern engines, the two of them are combined. Okay. Now, so let's take a look at these two different types of creating thrust force by using a propeller or by using jet thrust. Starting with the propeller one. So what's important about creating thrust force with a propeller is that the power output of the engine is reasonably constant with velocity. So this is a very, very important assumption, which is quite true, by the way. It's very reasonable to assume that, but in our performance calculations, this will be very important. So if you are using a propeller, then the engine has a certain amount of power, and whatever that power is, that remains constant with velocity. So let me insert a new page here. That means so I should use these actual thrust and power curves. Okay, so these are the required thrust and required power curves. And if you are using a propeller, then you have the power output of your engine more or less constant with speed. So that means if your engine can produce this much power, for example, then it remains constant throughout the speed range. So this is power available. For a propeller. Okay. Let me clean up all of this. Okay, so in a propeller engine, power generated can be considered to be constant with speed. If you plug power available from a propeller engine together with required power, this is what you get, as I showed here. So the available power is a flat line, but the required power is changing like that. And since you have this relation between power and thrust, then thrust available from a propeller is given by this relation. Okay, so the propeller available is a constant quantity, but the thrust available changes with velocity, and it can be found by using this relation. So if you look at this equation, you can see that a very high thrust force can be obtained at very low speeds, but at high speeds propeller thrust drops. So this is the available power, and if you divide this by speed, then you get such a relation. So these are obviously not really realistic, so I should have really prepared proper plots for this, but so this is the available thrust. And if you look at this relation, it seems that if the aircraft is not moving, such as when it's still on the runway, the thrust goes to infinity, but obviously that's not really the case. But still, you can say that you get the maximum thrust while the aircraft is not moving. But as the aircraft starts flying faster and faster and faster, the thrust drops. And so this is one reason why with a propeller aircraft you cannot really fly too fast, because the thrust you get from your engine drops as the speed is increased. But for very low speed flights, then propeller is a very good way to propel an aircraft. Okay. In the turbojet engine, on the other hand, this time the thrust output of the engine is assumed to be constant with speed. I should stick to these. So this time, again, we have the same thrust required and power required curves. Remember, this required power and required thrust, they have nothing to do with the engine type. These are related with the design of your aircraft. So whether you have a jet aircraft or a propeller aircraft, the thrust required and power required curves look all the same. But what differs between a propeller aircraft and a jet aircraft is the available thrust and power curves. So let me use a different color. So let me use this one, purple. So this time the thrust available is constant. So this is TA for a jet engine. Okay, and since you have again the same relation between thrust and power, then this is constant, but power then increases linearly with speed. So if this is your available thrust, then the available power will be going up like this, and this increases linearly with speed again due to this relation. Okay, so I don't know, I can't really explain why these are so, but for this course you need to just take these as assumptions. Okay, so if you are really curious as to why with the propeller power doesn't change and with a jet the thrust doesn't change, then I recommend you to read about this. Okay, so if you go online, if you make searches, I'm sure you can find very reasonable explanations for how or why these assumptions are made. But again, in this course you need to just assume these to be facts. So if you have a propeller, you have a flat line for available power, and the thrust changes like this. So where's the relation for that? Let me just show that here. So TA is equal to PA divided by V infinity. And if you have a jet engine, then this time you have the flat line on the thrust curve, thrust graph. So the thrust available is a flat line, and the power this time changes according to this relation. Let me write it here. PA is equal to TA times V infinity. And if you look at the jet engine, then you will see that the jet engine has very little power at low speeds. So at flying, so for an aircraft with a low speed, it makes no sense to use jet engine because you have very little power available. But if you look at the high speed performance of a jet engine, then it increases as the speed of the flight increases. So at high speed you have very high power compared to a propeller engine where the power is really limited. So you have very little power at high speed from a propeller, but for a jet aircraft it's the opposite. The jet engines are better at high speeds. Okay, so we will be making these assumptions, and to convince you that these are really true, let me show you again from some real data from real aircraft. So if you, for example, consider a jet aircraft, if you want to specify the performance of a jet engine, it doesn't make sense to talk about power because the power depends on flight, right? If you're talking about the jet aircraft, you can't say that it has this much power because how much power it creates depends on speed. At this speed it has this much power, but at a different speed it has different power, right? But the thrust is more or less constant. Okay, so if you are talking about the jet engine, then you should specify its thrust. So let's take a look at some data. So this is the Boeing 747 aircraft, the Wikipedia page for that aircraft. So let me show you the engine data for this aircraft. Let's go down to this these tables here. Okay, so some information about different versions of this aircraft are given, and what's important for us is the engines, right? So engine thrust per engine. See, the engine thrust is given, right? So these are all thrust values. It has the units of kilonewtons, and Newton is a thrust unit, right? So they give the engine thrust. So this is the maximum thrust the engine can produce. And so these are the different versions. So I guess this is the earlier version. It can produce, each engine can produce this much thrust force. Whereas if you look at the newest version, it can produce more thrust force, right? Per engine thrust force is increased. And yet this is, I guess, a future generation. Yeah, this is the newest one, and it has the largest thrust force available. These are the different types of engines. So when you are buying an aircraft, you can choose what type of engine you want, just like cars, right? If you want to buy a car, you can choose different options. You can get a diesel engine or a gasoline engine. You can buy your car with different engine sizes, right? 2 liters, 1.6 liters. And this is similar in aircraft. But in case of aircraft, there are different manufacturers as well. So if you want to buy a Boeing 747 aircraft, so if you have enough money, and if you go to Boeing and say that I want to buy a Boeing 747, then you can choose from different manufacturers. You can choose a Pratt & Whitney engine, or you can choose General Electric engine, or you can choose a Rolls-Royce engine. So they sell the aircraft with these 3 different engine manufacturers. And if you look at the numbers, they are similar performances. Okay. And if you consider an aircraft with a propeller, then this time giving the thrust information is meaningless, because this time thrust changes with speed, right? So you cannot say 10 kilonewton thrust aircraft, because that thrust is not a fixed number. And power is, for a propeller aircraft, power is a fixed number. So for aircraft that are driven by propellers, the engine specifications are given in terms of power values. So if you look at this aircraft, this is okay, so this is C-130 Hercules. It has 4 propeller engines. And if you look at the specifications for this aircraft, let me go down to that list. Okay, so the power plant information is given here. It has 4 of these engines, turboprop engines, and you see the engine power is given, right? Each of the engines can produce this much kilowatts of power. What is the power unit? So they don't specify the thrust here, because the power is really what is more or less constant with speed. Okay? Do you have any questions? So, by the way, we'll be calculating all these things in this course. The maximum speed, the range, service ceiling, rate of climb, takeoff distance. This used to be a part of this course, but I'm not really talking about that anymore. So the takeoff distance calculations are a little bit more complex. Okay, so let's see if there's anything else I want to talk about here. Okay, so this is really a good point to stop. Next subject is how these things change with altitude. Remember, all these curves depend on certain conditions, right? So let me go back and show you the equations. We have the equations for power. Okay, so this is the equation we use to draw the power curves, right? And if you look at here, it depends on certain numbers. For example, it depends on the weight. If you change the weight of the aircraft, then these curves will change because you have weight in those equations. Or if you change the altitude, then air density will change and these curves will change as well, right? So you have different curves for different altitudes and different weight values. And I will be talking about the altitude dependence next. But we don't really have too much time left, so I don't really want to start that subject today. Any questions? Okay, then let me stop here, and on Friday I will be talking about the altitude effects on thrust and power values. Okay, so I will see you next Friday.